So we are now looking at kind of coming to the culmination of this section. Now that we know what a differential equation is, now that we know how to write a differential equation and how to solve a differential equation, we're going to put it all together and look at an applied context where we can write our own differential equation, then go about solving it and using it to figure out a particular answer to a question given to us. So in this case, the question says, during one time period, the price of rhodium increased at a rate that was proportional to the price of rhodium at that time. So in the previous video, we talked about how to write proportional growth differential equations. The price for an ounce of rhodium was 475 initially, and it quadrupled every 25 months. What was the price for an ounce of rhodium after 18 months? All right, so let's start by writing our equation. We know that the price of rhodium increased at a rate that should be triggering the derivative. So the price of rhodium, let's call that R for rhodium, as a function of time. The price of rhodium increased, so the derivative of R is proportional to the price of rhodium at that time. So proportional, we have this constant of proportionality, times the actual price of rhodium, which would just be R of t at that given time. So what we can do now, we can go ahead and rewrite this. So what we're going to do is go ahead and solve for this differential equation R. We're going to use our initial condition to figure out the specific solution, and then we'll be able to plug 18 in to that specific solution to find our ultimate conclusion here. We said we will solve differential equations using separation of variables. To do that, we want to rewrite in Leibniz form. R prime is dr dt, and we know that it's equal to k times R, the price of rhodium. And I want to separate the variables here. So if I cross multiply, dr is equal to kr times dt, and then I would divide the r out. So I'd have 1 over r dr equals k dt. We'll leave the k on the right side. It doesn't really matter if we move it over, but I think it's a little easier if we leave it on the right side, the k on the right side. So now, once we've got the variables separated, this is where we said we want to integrate both sides to undo that derivative. And if we integrate both sides, we're going to see a really familiar pattern. As you do a few of these, you'll catch on to some very consistent patterns. And yes, you can lean on them as you pick up on them. But I'm going to work through the whole problem still. The antiderivative of 1 over r is the natural log of r. The antiderivative of k is kt. It's important to notice k is the constant of proportionality. It is not a variable. So the antiderivative of a constant is that constant times t. So the antiderivative of k is k times t. Of course, plus some other constant, c. And then we want to go ahead and solve for R, the price of rhodium. To do that, we need to undo the natural log. Well, that means we're going to exponentiate both sides, powers of e. So e cancels natural log, and we're left with r, which is equal to e to the kt plus c power. We already saw in the previous video that when I'm adding those exponents, I can really rewrite this as e to the kt times e to the c. And really, e to the c is just some other arbitrary constant. So let me actually write this in the next step. So r of t is equal to some arbitrary constant, e to the c, times e to the kt. What I need to do now is use the information that's given to me about the initial condition to figure out what that value k is. Okay, so I know that the initial price of rhodium was $475. The initial price would correspond to t equaling 0. 0 months have passed at the initial point. So at t equals 0, r of 0 equals 475. But then, after 25 months, we can see that the price has quadrupled. So when t equals 25, we would know that r at 25 would be equal to 4 times that initial price. So let's see, 1600 plus 300, 1900. Better make sure. Good. So we know we have 1900 is the price of rhodium after 25 months. So just right now we can say for sure that 18 months is somewhere between there. So we know the price is going to be somewhere between 475 and 1900. What we want to do now is figure out exactly what that price will be. So let's go ahead and look at this here. I have my general equation that solves the differential equation I started with is r of t equals c times e to the kt power. So let's take the initial condition we're given with, and we know that at 0, our price would be 475, and that's equal to c times e to the k times 0 power. So that would mean if k times 0 is 0, e to the 0 is 1, that c is equal to 475. So we have gotten one step farther. Our r function should actually be 475 times e to the kt power. We still have one issue. We don't know what k is. So now we can go one step further. And we can say, well, we can use the second condition we're given to figure that out. We know that r at 25 would be equal to 475 times e to the 25 is in place of t times k power. So we know that 475 e to the 25k is equal to this quadrupled value of 1900. And then we can use inverse operations to solve for k. So we would divide by 475. We would take a natural log on both sides to cancel the e. And then we'd have 25k equals the natural log of all that stuff. So k would be equal to natural log of 1900 over 475, all divided by 25. Right, we can type that all into the calculator in one shot. That would be natural log of 1900 divided by 475. Maybe you're catching on to the fact that this would be equal to 4 inside of that fraction since it's the quadrupling rate. Natural log of 1900 over 475 all divided by 25 is equal to 0.055. So k is 0.055. Okay, and this feels like a ton of work, but as you do just a couple of these, you'll start to catch the pattern here, and you can skip a lot. If you know the initial value is a certain value, you can kind of plug that straight into C, and you can go straight to this exponential model right here. You really can skip all the way straight to that. Once you get the hang of this and see it a few times, you're going to see a consistent pattern going on here. But for this one, I wanted to make sure we worked through the separation of variables and the actual solving of the differential equations. So now that we know what k is, we can rewrite our function r one more time, and now we have exactly what the function is. 475 times e to the 0.055t, and we were asked what is the value at 18 months. So we can just plug 18 in, we get 475 times e to the 0.055 times 18, 475 times e to the 0.0, if you want to be extra precise with your calculator, copy down the actual exact value, times 18 months. We get 1,288.77, roughly 1,289 in the actual problem here. So R of 18 equals $1,289. So again, that feels like a lot. There was a lot of work that went into it, but again, as you see the patterns developing, you'll be able to skip through a lot of it and go straight to the exponential to then be able to use a second condition to solve for k. So hopefully that's helpful in walking through some of these word problems. This is in Khan Academy under the differential equations exponential model word problems. The previous practice exercises were on exponential model equations. So this is just kind of repeatedly going through this first half that we did where you're just solving exponential model equations. So those are two good exercises. Take your time, practice them a lot, take advantage of the patterns that you recognize that keep repeating themselves. And that's a good application of when we can actually use differential equations in an applied setting.